Everybody, I'm Miss Marinelli. This is a little unorthodox, but we're going to try and make it work. So everybody in yesterday's class had an opportunity to have a quick review before the quiz, and I want to afford you all the same opportunity, but seeing how I'm not there, but you are, we're going to try and do something where you have a virtual review, sort of. So these questions that I'm going to show you are first and foremost exactly what we've been doing all year. In fact, if you look at this is nothing more than a bleacher ball question, just on a different planet. So what I'm going to ask you to do is take a second to read these questions and sort of pull out a piece of paper. And Miss Marinelli, would you mind pausing me while they pull out a piece of paper? All right, so everybody has a piece of paper. All I need you to do is, if you wouldn't mind, just please copy down BI, VF, AT, and D. And on your piece of paper, just do that, and we can try and make all this happen just as if I was there. So here's a sample problem. Many years into the future, humans land on the planet Zarth to conduct a bleacher ball experiment and determine the acceleration due to gravity. You did the same thing. So if the ball falls 15.8 meters in 5.6 seconds and the astronauts have no error due to reaction time, what's the acceleration due to gravity on planet Zarth? So I'm going to have you take a second. Miss Manarli, would you mind pausing me in a second? So would you guys take a second and fill out what you can fill in for VI, VF, AT, and D from the question here. So why don't you pause me now, and when everybody's done, why don't you look up Miss Marinelli, and she'll be able to keep going. All right, I'm assuming that you've all filled it out, and let's try and figure this out. So you can match with me. Ball falls 15.8 meters, so that looks to me like a displacement, and it's going down, so negative 15.8 meters in 5.6 seconds. So my time looks like 5.6 seconds, and we don't have to worry about reaction time. That's what this all is. So we're not going to subtract a quarter of a second for the fact that they were slow on starting the stopwatch. We're looking for the acceleration, and I hope you remember bleacher ball. How fast were you holding the golf ball when you let it go? And I'm hoping that you remember that your velocity to start with, or the golf ball's velocity was 0 meters per second. So something interesting here, I hope you match this first off, because if not, we're going to have a little bit of problems on the quiz. But I hope you match this. And second, we don't care about VF. I don't ask you about it. I don't want to know. I don't give it to you, so it's kind of dead to us. So what I'm going to ask you to do now is look at, turn your heads, look over at the, or actually for you, it's going to be this way. So turn your head that way and look at the Stanley Cup, or look at your equation sheet if you want to pull that out, and try and figure out which equation you can use that's got a VI, A, T, and D. Miss Marinelli, hit pause. And hopefully we figured out that we can probably use, I'm going to say D equals VIT plus 1/2 AT squared. And now it's a matter of just doing algebra, plugging and chugging. We know that D is negative 15.8 meters equals VI, which is 0, times T, plus 1/2 A, which is what we're looking for, times T, 5.6 squared. Now, a lot of people have a little trouble with their algebra here. I just want to make sure that you all are going to be okay with it. So the first thing that we need to do is, first off, get rid of this. 0 times anything, so 0 times T, which is 5.6, but that's just going to be 0. So we don't really need to worry about that. So negative 15.8 equals 1/2 A, 5.6 squared. And I hope you guys, please ignore me, and I'm going to work this out. Why don't you work this out too, and see if we can come to the same exact acceleration due to gravity. So Ms. Marinelli, why don't you pause it, and I'll keep going, and when you look up, we'll continue. So let's see here, 5.6 squared, that's where we have to start. If I can get my calculator going, 5.6 squared, that's going to be 31.36. So 1/2 a times 31.36 equals negative 15.8. Next thing that we're going to do is we are going to multiply both sides, we can multiply both sides by 2 to get rid of this half. And there are a lot of ways to do the algebra. You can do whatever you want as long as it's mathematically legal. Let's see, 15.8 times 2 is 31.6 equals, so the 2 times 1/2, that gives us 1a times 31.36. Very interesting. Looks like we're going to get a very interesting answer. Our next piece is we got to divide both sides by 31.36 and 31.36. And I'm actually going to erase this. We're going to have a is going to be 31.36 divided by 31.6 divided by 31.36, 1.007. Isn't that nice? You can round it, meters per second squared. Very interesting. This is a negative, which means this is a negative. And as we are dealing with negative acceleration, I hope you remember that acceleration means we're going, or negative acceleration means we're going down. I hope nobody had a problem with this. You've done this calculation before in your lab reports for bleacher ball, so this shouldn't be a big deal. Next up, again, take a look at this. When Miss Marinelli pauses it, try and fill in as much of the VI, VF, AT, and D as you can. And when you look back up, we'll continue. So Miss Marinelli, pause it now. And I hope that we've all figured out, speaking of reaction time, back here on planet Earth, a group of students want to see their reaction time. One student holds a ruler and drops it, which means the initial velocity, again, is 0 meters per second. And it falls 18 centimeters before the other student catches it. What's the reaction time? So on Earth, we've got an acceleration of negative 9.8 meters per second squared. And you can use negative 10 if you want. That's fine. But because we're back on Earth, we get to use Earth's acceleration. And we got this out of our bleacher ball experiment. It falls 18 centimeters, and this is the only tricky part. If you notice, I italicized and bolded it. Why would I do that? Because most of you will write negative 18 down here. Now I want you to remember what a meter stick looks like. It's about this big, and it didn't fall 18 of those. It's 18 centimeters, which means it's 0.18 meters, if you remember. So that's a little hiccup for everybody. And what is the reaction time? So I hope you remember and realize that we are looking for time. We don't care about final velocity, so that's kind of dead to me. VI, A, T, and D, we're going to use some equation. Miss Marinelli, why don't you pause it? And I hope you all figured out that the equation we're going to use once again is D equals VIT plus 1/2 AT squared. And we can just go ahead and plug and chug. So why don't you plug it in and Miss Marinelli pause it? And I'm going to plug stuff into negative 0.18 equals 0t, which we don't care about anyway, plus 1/2 negative 9.8 t squared. Negative 0.18 equals, let's see, half of negative 9.8. That's 4.9 negative t squared. And then what we can do is start getting through some algebra. Negative 0.18. Our next step is going to be divide both sides by negative 4.9. And that's very interesting that we have a pair of negatives. So that's going to go away. So we're going to end up with t squared equals negative 0.18 divided by 4.9 negative. we're going to end up with positive 0.036. Now, it is important because last time I checked, if you try and take the square root of a negative number, because again, we want the time, not the time squared, you can't take the square root of a negative number. Your calculator is going to give you an error message. And if you saw that, you didn't remember that you had two negatives here. So in order to take the square root, take the square root, take the square root on my calculator of 0.036. I'm going to round it. T is 0.19 seconds. And again, that's right in the realm of reason. Remember, average reaction time for a human being is a quarter of a second, 0.25 seconds, and we're dealing with 0.19 seconds. So you're a student, you're young, you're whatever, and you have a good reaction time. Congratulations. So I hope, again, there are no questions on this. You did an experiment on this. So the first two questions on the quiz are going to be an experiment or two experiment questions for you. Next up, again, why don't you take a second and read this and try and fill in VI, VF, AT, and D, and Miss Marinelli can pause it. And I hope that you've all realized car starts from rest and accelerates at a rate of 3 meters per second, so that's my A. 3 meters per second squared, sorry, 3 meters per second squared. For 13.7 seconds, and that's a time, 13.7 seconds, because we measure seconds, time is measured in seconds. Find the final velocity of the car. So I guess I want to know what the final velocity is, but was I a stinker and didn't tell you how fast it was going to start? Oh wait, I did. A car starts from rest. How fast are things going when they're at rest? 0. So why don't you take a look at this, VI, VF, ATE. I don't ask you about D. I don't give it to you, so don't worry about it. Turn your heads that way. Take a look at what the equation should be. Pause me. And we should have gotten an equation that is VF equals VI plus AT. And we're looking for VF, so VI is 0 plus A, which is 3. 3 times T, which is 13.7. And at this point, I guess pause me, figure it out, and let's see if you're right. 3 times 13.7 should end up with a VF of 41.1 meters per second. Actually, that's very important. I do need you to remember to put in your units when you're doing the quiz, because I'll take off because you're giving me naked numbers and we don't do that in physics. So there you go. Hope that wasn't too terrible. This is probably the easiest question that you'll see. Again, the questions are going to be very similar to this. I'm changing the numbers, so I'm not giving you the right answers here. But this is what we're doing. All right, and fourth question. Student starts riding a bike at a constant speed of 8 meters per second. She approaches her friend's house and comes to a stop with an acceleration negative 1.5 meters per second squared. So we've got a positive velocity with a negative acceleration. So we're going to slow down and stop, I hope, especially because it says we're going to stop. What's the displacement it takes her to stop? So take a second, read this over, fill in the chart, and pause me, and then push play when everybody's done. So I've got an initial speed of 8 meters per second because that's how she's riding. Meters per second. She approaches her friend's house, comes to a stop, so my final velocity is going to be 0 meters per second with an acceleration of negative 1.5 meters per second squared. What's the displacement it takes her to stop? Isn't that nice of me? I don't care about time. I don't give it to you, so we don't care about it. So now I need an equation. D, VI, VF, and A. Last time I checked, why don't you take a look at the Stanley Cup and hit pause. And I hope you figured out the correct equation to use is VF squared equals VI squared plus 2AD. Reason being, I got a VI, I got a VF, I have an A, and I'm looking for the D. And this is the only one that gives us those variables. All right, So at this point, why don't you take a second and plug it in, and I will plug it in too, so why don't you pause me. And I will say 0 squared equals vi squared, 8 squared plus 2 times negative 1.5 times d. So 0 squared is 0 equals 8 squared is 64 plus 2 times negative 1.5, negative 3d. And now I've got a conundrum. What do I do with this 64? I need to isolate the negative 3d, so I got to get rid of this 64. So I will subtract it from both sides. Minus 64 from both sides. Negative 64 equals, those go away, negative 3d. And the interesting part here is that we are going to now take our 64 and divide it by negative 3. If I get my calculator working, negative 64 divided by negative 3. Divide both sides by negative 3. Those go away. 64 over negative 3 is positive 21.3 equals my d, which is 21.3 meters equals my displacement. Again, it's really important that you realize that because we have a negative acceleration here, we get a negative number, and that allows two negatives to cancel out and make a positive. So the student is still going forward even though she's slowing down, and she will eventually stop after 21.3 meters. So I hope that helps, and I hope, again, this was not terrible. I mean, basically the physics is in here, realizing what's going on with the chart and choosing the correct equation, and then the rest of it's just algebra. So on the quiz, I'll give you partial credit if you do the physics right, you know, and you pick the right equation, and then if you kind of monkey up the algebra, I'll be kind of lenient for you. Next up is going to be some graph questions, and pay no attention to quiz. It's really not quiz. This was last year's quiz. But you're going to see something like this, and I'm going to ask you some pretty, I hope, easy questions on the quiz, and you can see I've got this all numbered. So the questions I could ask are pretty much anything. First off, we're dealing with a position, displacement, time graph. So displacement in meters and time is in seconds. So I guess the first question is there anywhere here that we're at rest? And if you remember anything about being at rest, why don't you on your piece of paper jot down where you see us at rest. So pause me. And if you see us at rest, we are at rest at 2. We are at rest at 4, and we are at rest at 8. And we're at rest at those 3 places because the slope is 0. And remember, slope of a position time graph is going to give you units of meters per second, which is velocity. So anywhere where there's no slope, there's no velocity. Where there's a positive slope, there's a positive velocity. Where there's a negative slope, there's a negative velocity. And the cool thing is, if you have a changing slope, you have a changing velocity. So I guess the next question would be, well, we know where we're at rest. How about where are we going with a positive constant velocity? And a positive constant velocity is going to say the slope is going to be positively constant. And there's only one place here that you've got a constant positive slope, and that is here. So positive constant velocity would be here. Why don't you answer this question on your own, though? Can you tell me where there's a constant negative velocity? So pause me, and you should hopefully see that there is nowhere here that has a constant negative velocity because nowhere here has a negative constant slope. So another question I could ask is, well, where are we accelerating? So you need to think about what does acceleration mean, and hopefully you would see where we're accelerating is anywhere that we're having a changing slope, a changing velocity. So why don't you pause it here and tell me where we see a changing slope. And hopefully you can see that there are changing slopes. We've got parabolas, which are the curves, which, you know, we're dealing with changing slopes at position 3, position 5, position 6, and position 7. So there you go. These are all of our different parabolas This is a negative acceleration. This is a positive acceleration. This one's opening down, so it's a negative acceleration, and so is this. So that's a little more tricky than I need you to really worry about. But realize when you're accelerating, you should see parabolas. When you're traveling with constant positive or negative velocity, you should see normal slopes, constant slopes. And where you see no velocity on a position versus time graph, sorry, I moved it, you should see flat areas. So that's a good thing to sort of have under your belt. And also, I feel like there's one place where I actually ask you to calculate the slope. It's very, very easy. The numbers are very simple to use. So there's one place I ask you to calculate velocity, and all you need to do is figure out the slopes for the places that I'm asking you about the velocity. So that's that position time graph. And the last thing that I could really ask you about is a velocity time graph. And here's one. This one looks a lot scarier than it is. But I guess the things I can ask again are where are we at rest? Where do we have constant velocity? Where do we have acceleration? Where do we have constant positive velocity? And where do we have constant negative velocity? So take a look at this, and I guess even also where are we speeding up? And where are we slowing down? So why don't you take a second and answer these questions based on this graph, and let's see what you come up with by yourself. But before you do it, remember that we're talking about speeding up and slowing down. This is your zero velocity. So the only point you're at rest is when you're actually here. And then you kind of have to think about what happens when you're speeding up and when you're slowing down. So if you want to, on your piece of paper, sort of jot these down and just put the numbers where you think you're at rest: constant velocity, acceleration, positive, negative, speeding up, slowing down. All right, so pause me. And welcome back. So let's start with at rest. Where are we at rest? Well, I see us with anywhere that we're touching 0, we're at rest. So we're touching 0 at 1. We're touching 0 at 5. We're touching 0 at 8. And we are touching 0 at 12. Okay? The cool thing is, all of those places are also where we're starting at constant velocity, because we are not really moving. Well, actually, 8 is not, but 1, 5, and 12 are, because they are straight, flat lines. Also, you have constant velocity where you have a straight, flat line at 3. 8 is not constant velocity because you are in the middle of changing velocity. So remember, constant velocity is anywhere there's a straight, flat line in the velocity versus time graph. 5, we're at a constant velocity, and also 10, we're at a constant velocity. Okay? Where are we accelerating? Well, we're accelerating anywhere that the velocity has a slope, anywhere that we have a change in velocity. So at the beginning here, we've got a velocity of 0. At the end, we've got something above 0. So 2, we have acceleration. 4, we have acceleration. 6, 7, technically 8 because it's on that line between 7 and 9. You're accelerating the whole way through here. Okay? You're slowing down, slowing down, slowing down, slowing down, stopping, speeding up, speeding up, speeding up, because you're getting further away from 0 velocity here and closer to 0 velocity here. And then there is 11, because you are changing your velocity here. Okay? Next thing, constant positive velocity. Well, that's where the slope is up. So that's pretty easy. Anywhere there's a positive slope, you're constant positive acceleration. So 2, 6, and 11. Constant negative, I'm actually going to take all of this and move it down because I'm getting kind of getting claustrophobic there. So there. So our constant negative velocity, oh boy, I broke the smartboard. There we go. Constant negative velocity is anywhere that we have a slope that's negative. So it looks to me that we got a negative slope at 4, 7, technically 8, 9, because they're all negative slopes, and that's it. Where are we speeding up? Well, that's where we're getting further away from zero velocity. So wherever, so 0, we're not doing anything. 2, we're getting further away from 0. So that's 2. We're getting closer to 0. 6, because we're getting away from 0 there. Closer to 0, 9, because we're getting further away from 0. Even though we're traveling in the negative direction, that just means we're going the other way. We are getting faster. And that's it. And then where are we slowing down? Well, anywhere we're getting closer to 0. So we're starting up here, and number 4, we're coming closer to 0. So we're slowing down, slowing down, slowing down. So slowing down is 4. 5, we're stopped. 6, we're speeding up. 7, we're slowing down. 8, we're stopped. 9, we're speeding up. So neither of those is slowing down. And then 11, we're going in 10, negative, 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 negative. 11, we start slowing down, slowing down, slowing down, and stopping at 12. So that's pretty much everything I could ask you. I'm not saying I ask you all of it, but I hope that kind of makes a little bit of sense to you. And you can look at a velocity time graph and sort of answer a couple of questions about it. I hope you can look at a position time graph and answer some questions about it. And I hope that your answers match up with mine. And if they don't, I hope I've explained to you why they are the way that they are. All right? So without further ado, pull out your calculators, pull out a good pencil, pull out your equation sheet. Miss Marinelli is going to hand out the quiz, and we'll give you probably about half the period to do it, because it is a pretty intensive quiz. Hopefully this helped you prepare for it, and after everybody hands in the quiz, you guys are going to be able to do a very entertaining lab. So good luck, and I will see you all on Tuesday, so enjoy your long weekend.